thing.
Oh yeah.
I'll
Oh,
have to
I
show
know,
you.
because your iPad is like an input device. You're writing on it. You're sending its contents to the meeting. So it's like you could just invite your iPad as a participant.
That's what some people do, and that's what I was going to tell her to try. Because I have seen mine, when I did that, it gave me a bunch of audio feedback, even if I muted both. So I don't know why, but.
Oh, yeah.
Okay, I'm sorry.
Are they going out a little or no?
I thought you were doing that.
Okay, oh, I am.
Hey everybody, how's it going?
Good, how are you?
Good. Just getting my stuff all going here. Everyone have a good weekend?
It seems like you've been in a different spot every single time.
That's true. I have
Almost.
a different spot every single time. I was outside this morning too, but then it got kind of hot, so I'm not outside anymore. But yeah.
Someone told me you were in Colorado.
I am still in Colorado.
That's really cool.
Yeah,
what are y'all doing?
We have an Airstream camper, those big silver camper thing, and we came up here in June, and then we're planning on coming back like at the end of July. But then when it was like, oh, school's going to be remote, it was like, okay, well then I'm going to stay here until we have to be back in school. So it's less hot here. It's hot right now, but hot like 90 degrees, not hot like 100 something degrees. So yeah, we just ended up staying for a while. Yeah, it's kind of awesome. Okay. We are doing our third set of notes. This is the last set of notes that are on your first problem set that's due Friday. And just keep in mind that problem set is not like one night of homework, so it will probably take a little while. Although this one is probably shorter because it's sort of easy stuff. It's like adding numbers and stuff. But I would try and start that sooner if you can than like Thursday night. Or else just give yourself more than an hour of time because it's a week's worth of stuff. Okay, so that is section 11.3 is what we're starting today, dot products, which I think you guys see dot products in pre-cal, but I don't know that you do very much. Like I don't know that you use it a whole lot. So yeah, the notes today will take probably more than the whole period. So I'll kind of like the first ones, I'll stop and then I'll finish the next day. They're not always like that, so don't like freak out and think that you have like bell-to-bell notes every single day in this class. That's definitely not the case. At the beginning it is, but calculus is like that too. So we'll have days where you have extra time or things like that too. So don't look at this and be like, why does this take so long every single day? I'm rushing through. It will not be the case. We're just kind of trying to cover the very beginning basic stuff, and sometimes that's what happens. All right. We already looked at simple operations that should be pretty familiar to you, like vector addition, scalar multiplication, stuff like that. They were all pretty simple. Today we're adding a new one called the dot product. It's also fairly simple. If we want to do a dot product, so like say we have A, B, C dotted with D, E, F, If we take the dot product indicated with a dot, all you do is you multiply the corresponding components. So like we would multiply the x components, a times d, the y components, b times e, and then the z components, c times f, and then we add them together. Okay, so pretty easy operation, multiplication, and then a little bit of addition, and you have your dot product. Notice the dot product is not a vector. Okay, I'll take two vectors, but after a dot product, it just becomes a scalar. I'll no longer have a vector there. And that's something that some people find a little bit confusing when they're doing multiple things, is forgetting that after a dot product, it's just a number. So you don't have a dot product, you don't have a vector anymore. So that's why I put this one on here. If you have these two vectors, when we add them, it's still a vector. Okay, the sum of two vectors is a vector. Scalar multiplication still gives us a vector. Okay, like 2 times a vector is another vector that's twice as long. But the dot product is a scalar, meaning a number. Meaning if it's put together with other operations, you're now down to like arithmetic, not vector operations. Once I do a dot product, it's not a vector anymore. So you won't do vector operations with it. Okay, so just keep that in mind as we kind of add stuff, do formulas, do different things. Oh, and there's a dog. Then we'll no longer have a vector there. Okay, so sometimes it's called an inner product or a scalar product. That I would just say, like, if you look in another textbook, or if you go online looking for like Khan Academy or other things to like give you more examples or give you more explanation if you're confused and you're looking, if you see things like inner product or scalar product, they're talking about a dot product. It's the same thing. I don't generally use those, but other books might, other courses might use that. So just be aware if you see inner product, scalar product, they're talking about the dot product. Okay, properties. So I mentioned this on the last notes. We'll basically always go over some properties. These are the basic rules that you know are true. So that if you're solving a more complicated problem than just a dot product, you know what types of things you're allowed to do. If you're looking at how a formula is derived, or you're deriving a formula, you know what types of things you're allowed to do. Okay, so dot products are commutative, meaning if I do the dot product of u and v, it's the same as the dot product of v and u. Okay, order is not going to matter. It's distributive over addition. So like if I take the vector u and I want to multiply it times the vector v plus w, I can use the distributive property, and that is going to be the same as u dot, oh, sorry, that's a dot product. U dot v plus u dot w. Okay, it's not associative, and really it's not associative more because you can't do a bunch of dot products in a row, rather than because it's not associative. It's because you can't multiply like u dot v dot w. You can't multiply in any order you want because you really can't do the multiplication at all. It's like if we tried to do this, the problem is after doing this first dot product, it's not a vector anymore. It's not a vector anymore, which means I can't do another dot product. The dot product is done between vectors. And after I do u dot v, I don't have a vector anymore. So it's not a dot product. So I can't do that. So it's not associative mainly because you can't do like 3 dot products in a row. After the first 2, you're going to be doing something with a scalar because you've got a scalar, not a vector anymore. Okay, you can do distributive property with scalar multiplication. So like c times v dot w is equal to cv dot w. Or if you'd rather, you could do V times C W. Be careful with multiplication, just the distributive property. It doesn't go to both, right? Like think if I do 2 times 3 times 4. If I distribute that, that's 6 times 4 or 3 times 8. But it's not 6 times 8. You don't distribute the 2 to both, right? You either multiply the 3 times 2 or the 4 times 2, then do the other multiplication. So if you want to ever like kind of distribute a constant, you distribute it to one or the other in multiplication, not to both, because otherwise you're multiplying by C twice. Okay, dotting with 0 vectors, so 0 dot U is the scalar 0. And then dotting a vector in itself. So U dot U, think if we had like components U1 and U1 and U2, and we dot that with the same components U1 and U2. We're gonna have U1 times U1 or U1 squared, and then U2 times U2 or U2 squared. And again, if it was 3-dimensional, you'd have a U3 squared or whatever. And notice that is the first step we use in finding the magnitude of U, right? I square the components, add them together, take the square root. And so this is equivalent to the magnitude of U squared, meaning the magnitude of U without the square root. Froze or something. Hold on, I'm gonna stop the screen share because it seems to have frozen partway through writing that. And then let's restart it here. Okay. All right, there it is. So it's the magnitude of U squared. It's the equivalent statement there. So where you see U dot U, you're getting the square of the length. Basically the length without the square root. Okay, and we're gonna use some of those properties right now to develop a formula for the angle between two vectors. This is one of the main applications of the dot product, is getting angle information. So if we have U and V and we want to know the angle in between, what we're going to do is we're going to close this in and make it a triangle. Since U and V are not head to tail, that third side is not U plus V, right? Since we're basically head to head, it's actually a difference. And so since we're going the same direction with U and opposite with V, so I'm gonna think of V as going this way and make it a negative V, so that they're head to tail, and this is negative V plus U or U minus V. Right, since now U and negative V are head to tail, it's the sum of those two. And then I'm gonna use law of cosines to derive. We're not using law of cosines to solve this usually, but I'm going to use law of cosines to derive the formula that we're going to use for angle between two vectors. So law of cosines deals with basically any triangle we want. We have triangle ABC. Opposite angle A, we have side A. Opposite B, we have side B. Opposite angle C, we have side C. And remember, law of cosines, you start with any side you want. Usually, like for us, we're going to start with the side opposite the angle we're interested in. So like, say I want angle A, I'm going to start with side A. And it's basically Pythagorean theorem. A squared equals B squared plus C squared. But since it's not necessarily a right triangle, we have this extra quantity that you should have seen in pre-cal, where this comes from, but minus a 2bc cosine A. And so just notice this angle is opposite this side over here. You could otherwise start with any side you want, and just you would move and use the angle opposite that side. So we're going to use law of cosines and derive a formula for an angle here. So since we're interested in theta, we're going to start with side U minus V. And since we're doing lengths, side lengths, we're going to use the lengths of these vectors. So the magnitude of U minus V squared equals the magnitude of U squared plus the magnitude of V squared minus 2 times the magnitude of u times the magnitude of v times the cosine of the angle theta. Okay, so that's just law of cosines with the lengths of the sides. On the left side, we're going to use one of the properties from the previous page. The magnitude of u minus v squared is just u minus v dot u minus v. Right, the very last property we just saw is the magnitude of a vector squared is just the dot product of that vector and itself. On the right-hand side, we're not going to change anything, so I'm just going to leave that alone for right now so I don't have to rewrite all that stuff. And then we're going to use another property from the previous page. So this is where those properties come in. It's usually deriving formulas and things like that. I'm going to use the distributive property. So it was, I said with addition, really addition and subtraction, same idea. So I'm going to use it over here. So I'm going to have u dot u. And then I'm going to have a u dotted with a negative v, so a negative u dot v. And then I'm going to have a negative v dotted with a u, so a negative v dotted with u. And then a negative v dotted with a negative v, which is going to come out as a positive v dot v. And again, I'm going to leave the right-hand side alone for right now. And use some of the properties from the previous page again. U dot u is the magnitude of u squared. U dot v and v dot u are the same, right? Commutative property is true. So this is minus 2 u dot v. And then v dot v is magnitude of v squared. Now I am going to write the right-hand side because now I'm going to simplify some things here. So we didn't change anything on the right-hand side, so I'm just rewriting the whole right-hand side. But notice all those dot products and those magnitudes, those are all just numbers. They're not vectors anymore. So I'm literally going to simplify this like you would arithmetic or algebra problem. So I'm going to subtract the magnitude of u squared from both sides. Notice it's on both sides of the equation. I'm going to subtract the magnitude of v squared from both sides because it's on both sides of the equation. And now notice a factor on both sides is a negative 2. So I'm going to divide by a negative 2 on both sides of the equation. And so I'm going to have that u dot v is equal to the magnitude of u times the magnitude of v times the cosine of theta. Okay, and that's essentially our formula that we're interested in. Only we're usually looking for the angle, so a lot of times you'll find it having solved for the cosine. Oops, u dot v, that's a u, sorry. Over the magnitude of u times the magnitude of v. Okay, and that'll give us a cosine of the angle between the vectors u and v. If we were to use unit vectors, notice these are unit vectors here. Then we don't have to divide by anything. So if we used unit vectors going in the same direction as u and v, that's what's in the formula technically. The way we write it, you don't need a unit vector because we divide by the magnitudes and make them unit vectors. But that'll give you the cosine of the angle between the vectors. You obviously don't have to do all that work every time, but that's where the formula that we're going to see comes from. So we usually see this, and I don't really make you memorize any formulas. Tests are open note. As long as you know how to use the formula, you should be in good shape. And as long as you have a place where you've written them down in a place that's useful. If you want the actual angle, obviously this is giving us a cosine of the angle, meaning you'll get a number between 1 and -1. If you want the angle itself, you would take the arc cosine of whatever quantity you get there. And then that'll give you the angle itself if that's what you're interested in, which a lot of times it is. If it's not a unit circle value, you need a calculator or something. Okay, so, oops. Can you still see my screen? Went away. Oh, there it is. So alternative form would have been if we had stopped one step sooner. The alternative form of the dot product is that we can use the magnitudes and the angle rather than the components to find the dot product. Oh, it's frozen again. Oh, there it is. Okay, if we had stopped a step before on that derivation, this is called the alternative form of the dot product. And it's finding the dot product using the angle and the magnitudes rather than the components, right? If we knew the lengths of u and v and the angle between, we could take a dot product by just multiplying these quantities as well. That's useful in experiments, in like real world science, engineering problems. You often don't have components. Like that's a very perfect world math thing to want, is a bunch of component form vector things. We usually have instruments that can measure things like a magnitude of a force, 200 pounds, or an angle between them with things like protractors and compasses and all sorts of different tools for measuring angles and magnitudes. A lot of times that's what we have. So we can do dot products using those quantities rather than the component form if you don't have a component form, which again, really common in science, that you, with instruments, measure these quantities, not the component forms of the vectors. So that's also useful there. It also tells us something about the angle, even if we don't have a calculator and we can't calculate that angle, we know something about it. The biggest one is going to be if we get u dot v equals 0. Okay, and let's assume u and v are not the 0 vector. Okay, if we look at this dot product, if u and v are not 0, their magnitudes are both going to be positive, right? Magnitude is length. So both magnitude of u and v are positive numbers. So the only way u dot v can give me 0, if I have a positive number times a positive number times a cosine theta, is when cosine theta is 0. Meaning when theta is 90 degrees or pi over 2 radians, right? The only way you're getting a 0 from a dot product of two non-zero vectors is when cosine theta is 0, right? This is the thing that's going to influence, since I have a positive times something, you're only getting a 0 if that third thing is 0. Okay, we can also tell if we get u dot v is positive. Same idea, if I have a positive times something, that number is going to come out positive when cosine theta is positive, which from the unit circle, cosine theta is positive over here. So when theta is acute. And then if you get u dot v is negative, that means the cosine part's over here, theta is obtuse. Right? Since magnitude of u, magnitude of v are positive, it's that cosine that's affecting the whole product coming out 0 or positive or negative is basically what's happening with cosine. So if we take a dot product, we can tell some information about the angle, even if we don't have a calculator and can't calculate the exact angle itself. Okay, that first one's going to be pretty important because that's how we find what are called orthogonal vectors. Orthogonal vectors are two vectors that meet at a right angle. In 2 dimensions, that's pretty easy to tell. Once you get any higher, it's not quite so easy just by looking at a problem. But it's still pretty easy because we can use dot products. So like u dot v gives 0 means u and v are orthogonal or meet at a right angle. So you can tell pretty quickly if you have like 1, 1, 1 and 2, 3, -5. Those are orthogonal. So if I take the dot product, I would get 2 plus 3 minus 5 is 0. So those are orthogonal vectors. And the easiest way to tell is just take a dot product. 1 times 2 plus 1 times 3 plus 1 times -5. I get 0. They're orthogonal. Meet at a right angle. And dot products are pretty easy. So a lot of times if that works to do something, that's a pretty simple way to do it. In terms of orthogonal, perpendicular, and normal are all essentially the same idea. It means things meet at a right angle. Perpendicular, you guys have seen a lot. Since maybe pre-algebra, you've been seeing perpendicular. Orthogonal, you probably haven't seen as much, and normal, same idea. I'm fine with you guys interchanging those. It doesn't really matter to me. You want to make sure you recognize the 3 terms all meet at a right angle, so that if you encounter them in a homework, in a notes, again, if you're looking at outside materials for more help, that you understand those are basically means meet at a right angle. They're used specifically, perpendiculars used between geometric shapes. Okay, lines are perpendicular to planes, or lines are perpendicular to lines, or planes are perpendicular to planes. Orthogonal is used between vectors. So vectors are orthogonal to each other. And then normal is, we saw in calculus, a normal line is a line that's perpendicular. Usually that's used between a vector and a geometric thing, like a vector and a line, or a vector and a plane, or things like that. So just know that if you see those terms, they basically mean the same idea. Okay, so find the angle between U and V. So we'll just use that, oops. The cosine of the angle is U dot V of the magnitude of U times the magnitude of V. And so U dot V, I'll just go component by component and multiply. So 3 times -4 is -12. -1 times 0 is 0. And then 2 times 2 is 4. Magnitude of U, I square each component, add them together, and take the square root. So I'll have the square root of 3 times 3 is 9. -1 times -1 is 1. And 2 times 2 is 4. And then for V, same thing. -4 times -4 is 16. 0 times 0 is 0. 2 times 2 is 4. So I have -8 over the square root of 14 times the square root of 20, which is obviously not a unit circle value, okay, not one that you would necessarily know. At that point, for the angle, I would enter it into a calculator. So you take the inverse cosine. We could simplify it a little bit, but simplifying isn't going to give you a unit circle value, so I would just use a calculator at that point. Put that into the inverse cosine. I don't have my calculator, so I don't know what it is. I do know it's obtuse. Since it's negative there, I know it's an obtuse angle between the two vectors, but I don't have my calculator, so I can't tell you what it is. But put that in a calculator, take the inverse cosine, and there's your angle between U and V.
Mr. Smith?
Yeah.
Will we be using degrees or radians? I know a lot of the homeworks have had degrees, but we usually use radians.
It doesn't really matter until you're doing calculus stuff. So the main reason that we use radians in calculus is all of the formulas that we learn with derivatives and stuff are derived using radians. So as long as you're not taking a derivative, it doesn't really matter, and you can kind of choose. It doesn't matter to me. Yeah, it's kind of up to you guys until we are doing anything with derivatives of trig. Those formulas that we memorize, the derivative of sine being cosine, is only true in radians. It's not true in degrees. So yeah, that's the only thing that matters. So otherwise, you guys can choose. If the homework says 180 degrees and you want to use pi radians, that's fine. It doesn't matter. Okay, so this one, if you guys are careful and pay attention, you could find things that are shortcuts. So like this one, you have 2 options. So if you're really observant and paying attention, oops, and we notice that V is -2 times Z, which we learned means they're parallel to each other. They're actually going in opposite directions, but they're running in the same line. What we basically mean there then is V is going one direction, Z is going the opposite direction. Okay, so they're going in opposite directions. So if you think about it, if you have one vector as a multiple of another, either they're going in the same direction and their angle is 0, or they're going in opposite directions and their angle is 180 degrees or pi radians. So you can use shortcuts like that if you notice them. Okay, if you don't, we can do what we did before. Take the dot product of V and Z and I get -8 plus 0 plus a -2 over the square root of 16 plus 4 times the square root of 4 plus 1. So it's -10 over the square root of 20 times the square root of 5, which is -10 over the square root of 100, which is -10 over 10, which is -1. And we should know the cosine of theta is -1 at 180 degrees or pi radians. So you can use the formula, it'll still work. But if you notice things that where you're like, oh, I can tell these are running in the same direction, the angle is going to be 0, or these are running in opposite directions, the angle is going to be 180 or whatever, you can use that information as well. Just know if you don't notice, it doesn't mean you're wrong. You can still do the formula and it'll still work. Okay, as far as direction goes, I don't remember if it was this class, but somebody asked me, how are we going to tell direction in 3D? If 2D, we talk about it from the positive x-axis counterclockwise, that's not very meaningful in 3 dimensions. Because are we talking counterclockwise like this, or like this, or, you know, we could be running counterclockwise going in all sorts of directions. If we're not on a plane, saying we're going to go counterclockwise doesn't really make sense. So in space, 3D space, we actually talk about it as 3 angles. So think if you know how like your phones and stuff can find your location. Some of them use GPS satellites and stuff like that, but some of them it can also triangulate you from towers. If it can find the 3 cell phone towers and how far you are from each of those towers, it can find exactly where you are. It's called triangulation. We can do the same thing with angles, and instead of from the positive x-axis, we do the angles with each of the positive axes. So the angle from the x-axis to our vector, from the x-axis to our vector, from the y-axis to our vector, and from the z-axis to our vector. If we know those 3 angles, it will put us at one specific direction in space, pointing in one direction. So if we find the angle between the positive axis around of each of the axes, we'll find our location. So these are called the direction cosines, and there's 3 of them. There's alpha is from the x-axis, beta is from the y-axis, gamma is from the z-axis. Those are your 3 main kind of cardinal directions. We won't use this a ton. It is something people use to refer to the direction of a vector. But in general, for most of our math, we don't need those angles. We need a vector to describe a direction. So usually it would be like, oh, I need something going in the direction of vector V. We use V itself to kind of give us a direction. So we don't often use this in this class. Other classes use it. You want to be aware of them. We're going to go over how to find them. It's not very difficult. We've never talked about finding angles between a vector and a line or an axis, but we did just talk about finding directions or angles between vectors. So instead of thinking it as the angle between V and the x-axis, think of a vector on the x-axis or running the same direction as the x-axis and find that angle instead. easiest one is I, our unit vector going 1, 0, 0. Right, if we find the angle between V and I, that's the same as the angle between V and the x-axis because I is parallel to the x-axis. Same thing for the other ones. We can find the angle between V and J and V and K using our vector angle formula. And so that's how we find our direction cosines. We're going to go ahead and derive those formulas. They're really simple. And again, we aren't going to use them a ton. So you want to have somewhere where they're written down, where you understand how to find them, what they're talking about. But it's not something where you're going to have to use it so much that you're going to want to memorize them or anything. Okay, so remembering that I is 1, 0, 0. Oops. K is 0, 0, 1. And J is 0, 1, 0. And let's say V is any vector, V1, V2, V3. Okay, for the x-axis, we're going to find the cosine alpha, which will be V dot I over the magnitude of V times the magnitude of I. Okay, V dot I, because we chose a unit vector I, we could have chosen any vector like 5, 0, 0 or 1,000, 0, 0. It would give you the same thing. Because we chose a unit vector, it makes it simpler math. Because notice V dot I will be V1 times 1 plus V2 times 0 plus V3 times 0. The magnitude of V, we'd find the same way, square root of V1 squared plus V2 squared plus V3 squared. But then again, notice magnitude of I, it's a unit vector, so it's 1. So to find the cosine of alpha, we literally take the x component of V over the magnitude of V. For the y-axis, we do the exact same thing, but notice we'll use J. So instead of leaving us V1, it's going to leave us V2. We did the exact same thing. Oops. It'll be V2 over the magnitude of V. And then for the z-axis, cosine of gamma, same thing, V3 over the magnitude of V. So it's pretty easy. And just like our other angle formulas, you're getting a cosine of an angle. So it's not actually an angle. It's a direction cosine, meaning you're going to get little decimal numbers and stuff there that will give you the angles. So we wanted the direction cosines. Cosine alpha will be our x component 2 over the magnitude of our vector, square root of 2 squared plus 3 squared plus 4 squared. Oops, 4 squared, saying 4 and wrote 4. So 2 over the square root of 29. Cosine of beta is the y component over the exact same magnitude. And cosine of gamma is the z component. Oops. Over the same magnitude. So those are the cosines. So if it says what are the direction cosines, that's it. You'd stop there. If you want the actual angles, which this problem also asks for, you would do the inverse cosine of 2 over the square root of 29. The inverse cosine, this is going to give you alpha itself. The inverse cosine of 3 over square root of 29. And the inverse cosine of 4 over square root of 29. So a problem may just ask for the direction cosines. That's just the column on the left. If it also wants the angles or the angles instead, that would be the column on the right. And again, you'd use your calculator. This one I can tell you they're all acute because they're all positive. I don't have my calculator, so I can't tell you exactly what they are, but they're all acute. knowing the location of this, you should know they're going to be acute. Because notice it's in the octant where x and y and z are positive. So it's in the octant over the positive, 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 which means the angles between the positive axes will all be even. Acute angles, which we can also tell from the direction cosines. Okay. The last thing we're going to get to, and I probably won't finish the last examples because we are running low on time, but I'll finish the examples tomorrow, is we've already looked at how you can add vectors to find a resultant. So we have like vector u, vector v, and then we'd say this is u plus v, which we call the resultant, the sum of some vector forces. Again, similar to the alternative form of the dot product, if you're in like some real world science application, you often don't have u and v. You have the instruments where I can measure the resultant. I measure the force that's occurring. I measure the direction of the force that's occurring. I usually can measure a resultant in a scientific application, an engineering application, a physics application. I have tools to measure resultant. But sometimes I want to kind of reverse and find the components that make it up. So I might have some big force, and I want to kind of go backwards and find the little forces that are making up that big force. Okay, the little forces that are contributing to that big force. So we call that decomposing into vector components. So it's like, I know this big resultant force, and I want to know what things are contributing to that. So I want to kind of go backwards. So really common in an experiment type of a setting. So consider an example like you're pulling a boat up a ramp at the lake. And what we usually know in this situation, like manufacturer will tell you, is the weight of the boat and the weight of the trailer, right? Basically gravity will contribute to the mass, pulling towards the center of the earth straight down. Okay, when we're looking at like what type of a truck we need, we don't need to pick the trailer up this way, right? The mass is not as much of an importance as we need to make sure we can counteract what's happening that way, right? If you look at like YouTube videos, there's all sorts of videos of like people using cars that are too small to try and pull a boat, and it pulls the car and the boat down into the lake. We're interested in kind of the force pulling down the ramp, which is a chunk of the mass, right? Part of the mass is pulling down. Part of the mass, and I didn't make this as angled as I really should have because it's not going to look very good. Part of it's pulling into the pavement, right? Part of that mass is holding the boat on the pavement. Part of the mass is trying to pull you down the incline of the ramp. So if we're picking a truck, we're kind of interested in this piece. If we're picking a trailer, we're probably actually interested in this piece. Can the suspension support that part that's pulling you into the ramp or whatever? So you're kind of breaking this huge force that we know down into smaller pieces. So this is a better picture because it's got an angle on it. So picture this would be that mass. Okay, the main force pulling you towards this earth. Okay, whether you're on an incline or not. And so here W1 would represent the force, the part of that mass pulling you down the ramp. It's not the full weight of the trailer and the boat. A part of that weight is pulling you into the ramp. Part of you is pulling it down the ramp. W1 would represent the part pulling you down. W2 would be the part pulling you in. Add those together and you get the full mass that's happening there. Okay, so that's what we mean by decomposing, is taking some big force and talking about what are the little smaller forces that make that up. And so that's me projections, and we're out of time, so I'll go into projections and finish this stuff tomorrow. But that's where we're going to kind of end. Projections are big in this class, but they're also big in linear algebra next semester. So that'll be something that we'll need. So for now, I'm gonna let you guys go since it is 12:30 and it's probably either time for lunch or it's time for your next period. Either way, it's time for you guys to have a break. So I'm gonna let you guys go and have your break. And tomorrow we'll finish this stuff, and it should be plenty of time for you guys still to do your problem set and stuff like that. So you guys have a good afternoon, and I'll see you guys tomorrow.
Thank you.
Thank you,
Bye.
Mr. Smith.
Thank you, Mr. Smith.
Yeah, bye, you guys.
Mr. Smith, since I just switched into this class, could I have the Google Classroom?
Yeah, it is. Hold on just a second. This is third period. It is here. So let me just put it in the chat so you can like copy it or whatever.
Okay.
So that's the code for this class.
Okay. Okay, thank you.
You're welcome. Have a good day.
Me too.
Bye.